Okay, right now I'd like to introduce to you the VP of Sales and Marketing at Jayhawk Fine Chemicals Corporation, Boris Shafran. Boris holds a degree in chemical engineering and has over 30 years of industrial experience with raw materials and formulated systems for specialty coatings and composites. Boris, welcome to today's event, and with that, I'm going to hand it over to you to get us started.
Thank you, and good morning. This is Boris Shafran with Jayhawk Fine Chemicals, and we'd like to spend the next 30 to 40 minutes with you to present a summary of findings from an investigation that we've been working on as a collaboration together with a number of partner companies, and these include Ivana Corporation, Dixie Chemical Company, and Crosslink Technologies. And together with Jayhawk, we've been talking about and we've been wanting to investigate for some time and gain a better understanding of not only classic epoxy-anhydride systems, but how they can be modified and formulated with different types of accelerators, different classes of accelerators, in order to make them more suitable for applications that really have been brought to our attention from different customers and different inquiries, looking at things like faster curing cycles, lower curing temperatures, types of things like this that the information, while it may be available in the literature, it's certainly scattered throughout. There's a lot of empirical findings that people draw upon, but there really isn't one single place where someone can go and take a look at how do I formulate, what are some key tips that would be suitable to my particular project. And we think we've captured a couple things here, and we're happy to share them with you today. As I go through the presentation, I certainly welcome you to start thinking about comments and questions that you may have, and please submit them throughout the course of my remarks. At the conclusion, we're going to have a Q&A session, which will include some of our other collaborative partners, and I'll be happy to field your questions and have a general discussion. So thank you very much, and I look forward to sharing with you this new information that we've developed. So let's take a look at today's program. The first thing we're going to talk about are the benefits and successes, the value that epoxy-anhydride systems bring to a host of different applications and in different markets. Some may know this very well. Others I'd like to just introduce this to so that we have a good foundation. What's more important is the new challenges that have been presented to us and to the industry as a whole, because the merits of epoxy-anhydrides can be applied to a lot of newer applications. The question is how. And so we'd like to identify these and discuss them with you. Next, we'd like to move on to just a quick primer where we go through the classic mechanisms of epoxy-anhydride cure so that we all have a good foundation and a good understanding of how these reactions occur and what are the issues regarding the cure mechanisms. We will then move on to how do we adapt this classical chemistry, and in this case we're talking about accelerators and different classes of accelerators, some that are go-to products that are known, others maybe a little bit more unusual, and how can we adapt the classic chemistry to work in more stringent or more demanding type of processing conditions. The results that we obtained, and this has been done primarily through DSC work, which we will describe to you, has been really encouraging, and we found a couple of very interesting things, and we're very much looking forward to sharing it with you. Because of these results, we're able to put together a nice little summary of key tips, things that you can look out for as you consider formulating these type of systems for your individual projects. Now, this work has also uncovered some additional things that we'd like to take a look at as well, and this forms the basis of future work, which we would be considering, for a subsequent investigation and subsequent sharing with you. We then like to wrap up with some conclusions. I would also like to recognize my colleagues who have served as collaborative partners on this project, and then we'll open it up for questions and answers. Great, so let's move on to benefits and successes. And here I mean more the legacy applications where the value of epoxy-anhydride cure systems have really been demonstrated. Epoxies, especially the bread and butter type resin formulations, the DGEBA class of resins, they respond beautifully to anhydride curing, both mono and dianhydrides, and these have been used on a regular basis since the 1960s. And the value that they've demonstrated is their ability to retain certain physical, mechanical, and electrical properties under high temperature conditions for long periods of time. And where this has worked the best is a variety of electrical applications, as you can imagine. Different formulations such as two-component adhesives, coating powders, molding compounds for all types of small electrical circuitry and devices, wiring varnishes and enamels for electric motors, mass cast insulators, so inorganic filled polymers that are used as insulators for overhead power lines, for example, and different infrastructure applications, including fusion bonded epoxies for anti-corrosive coatings for surface protection, syntactic foams, which are an intriguing class of composites used for thermal insulation. These have all translated into and now have a modern relevancy. And these include things like smartphones, certainly the ones that have been around since the advent of the iPhone in the mid-2000s. There are a whole host of components and circuits within these type of devices which would extend to tablets, certain notebooks, and now wearables which are being developed, all utilizing the performance benefits of epoxy-anhydride cure. Electric and autonomous vehicles, which require just a greater demand for not only electric motors, but wire and cable, display systems, telematics. So this is a perfect application where the technology can perform. Home and industrial lighting, specifically LED systems, where the diodes require encapsulation with a water-white epoxy. And energy exploration, where I referred to before the syntactic foams. These are now finding use as a very effective thermal insulator, specifically for rigid pipe used for deep water applications. So the basic value that these epoxy-anhydride systems provide have now been used for a variety of different applications, starting primarily in the electrical area and now moving into a variety of different uses and applications. With the new challenges then come a host of new requirements, not only from the processing, but in some cases the property side. What has been traditionally understood as the current practice and the legacy practice, things like curing temperature, where 200 degrees C would be a typical temperature that's encountered for curing. Now, questions are being asked, can that temperature be reduced to as low as 180 C? Can we get it down to 140 C? Still make a viable polymer that could be useful for these applications. Hand in hand with that is the curing cycle. Can the productivity be increased? Can we get greater throughput? By how much can we reduce the curing cycle? Heat resistance, which is pretty much a standard property for the epoxy-anhydride type of chemistry. The greatest TG development you can get is an epoxy which is cured with a dianhydride, for example. Can that heat resistance, which implies that there is a high degree of cross-linking density and unfortunately in some cases a high degree of rigidity, can that be dialed back? Can I have a reasonable amount of heat resistance with a little bit less rigidity? How do I do that? In the case of color, which may have been tolerated in the past, especially, for example, let's say, pigmented coating powder formulations, now we're looking at water-white applications such as LED encapsulants. And how do you achieve that? The use of inorganic fillers, which is practiced with electrical insulators, pretty standard mass cast type of process and formula, What about the use of fiber composite materials, which would include carbon and glass fibers, for example? Molding powder formulations, pretty standard, pretty traditional, well understood. Now what is being asked is, can this technology be transferred into pre-preg formulations? What about bulk or sheet molding compounds that have their own issues with regards to things like shelf life, for example, or processing? How does this technology transfer into these new requirements? And this is what we've looked at with our study. Before we continue, I'd like to take a moment and review the classic epoxy-anhydride curing mechanisms, of which there are 3 reactions. What's important to consider is that anhydrides do not react directly with epoxides, as is the case with other type of epoxy curatives. In this case, we have the anhydride which seeks out a hydroxyl group, and this could be present either on the resin backbone. It could be introduced as alcohol, as added water, or could also be a contaminant within the system itself. These 2 constituents react and form the monoester, which is then required in reaction 2. This is the group which does react directly with the epoxide and forms the diester. The diester is the essential component which is required for propagation and formation of the 3-dimensional network and the epoxy polymer. In some cases there is a reaction 3, which is less favored, and that involves the combination of an epoxide with a hydroxyl group. With the curing mechanisms understood, it's time to take a look at how to adapt the chemistry to affect some of the changes that we've been challenged with. This represents an overview of all the materials used in our study. We start with the epoxy resin. We selected EPON 826, which is a classic DGEBA resin. This one has a slightly lower viscosity to facilitate mixing of ingredients. From the anhydride class, we looked at benzophenone tetracarboxylic dianhydride, BTDA, which is a classic dianhydride in powder form. Natick methyl anhydride, a well-known monoanhydride in liquid form. We also looked at synergies between the 2, and we created a blend which actually is a homogeneous, easily processable paste. From the accelerator side, we looked at 3 different classes. Some of these are well-known, perhaps everyday products. Others a bit more unusual, to see what kind of results we could obtain. From the tertiary amine class, we selected benzyl dimethylamine, BDMA, an everyday product in liquid form. From the imidazoles, 2-methylimidazole and 2-phenyl-4-methylimidazole, both in powder form. And from the urea class, we looked at dimethyl phenylurea, a accelerator in powder form. It was important to come up with systems where we could optimize results, and while at the same time, frankly, dispel some of the myths about the epoxy-anhydride chemistry being an older, perhaps even obsolete technology. If anything, it's become highly relevant to address some of the modern applications that we've discussed. Here's the design of experiments for the 12 formulations that make up our study. Here you see the different amounts of resin, accelerator, and curative included in each formulation. In some cases, the amounts are based on stoichiometry. In other cases, they're slightly off the stoichiometry. And in yet other cases, they represent recommended values. The reasons for this and the explanations will be provided as we go through the different results, which we will present to you shortly. The data for our study was generated via differential scanning calorimetry. We looked at 2 runs per formulation in order to verify reproducibility, and overall this was excellent. In some cases, if there was concern, we would add a 3rd run to validate the data. We focused on dynamic scans. These were run at 5 degrees per minute, in order to generate a series of different events. And these events correlate very nicely and allow us to have a good understanding and make an assessment of the viability of these different formulations with regards to processing conditions, overall curing efficiency. In some cases, we looked at glass transition to make a further judgment on the performance of the systems. We generated quite a lot of data. In today's presentation, we have condensed it down into a series of results and tips that we're very excited to share with you. So the results that we obtained were quite encouraging on a number of different levels. If you look at expectations and the results that we got, in some cases very favorable, in other cases still more challenging, we uncovered a lot of things that we hope are very useful for you. Let's look at stoichiometry. Every engineer and chemist will do their proper stoichiometric calculations to determine the right amount of resin and curative for their formulation. What's important to understand with anhydrides is that actually less is more. There are a lot of empirical methods which are sometimes used to calculate these, but the understanding is that the numbers that you determine should be slightly dialed down because of the reactivity of the anhydride groups. The result is that less is always going to be more for you. We'll demonstrate that in a moment. Mixing difficulties. Yes, there are a variety of different constituents which we're trying to combine. Some are solids, some are liquids, some are pastes. The first reaction would be that this is too difficult to do, and you will never get homogeneity in your systems. What we found is that a very simple and gentle heating of ingredients at 35°C facilitated this mixing. A very easy answer to what looks like a larger concern. Formulation complexity. We've presented 12 different formulations to you, but the fact is that they are quite simple in their approach. We're not adding more than we need. We're not adding more ingredients than we need. We're focusing purely on resin, curative, and accelerator. This allowed us to really understand the behavior. So it's important here for everyone to understand that simpler is quite often better, especially when you're putting formulations together. There are many cases where people add so many things, after a while they don't even understand why the things are in there. So, homopolymerization, which is quite prevalent, and we discovered it in many different formulations. It can actually be enabled, and it can be at least controlled to a certain extent. And we found that to be a function of the different accelerators that we used. Very interesting results. We'll share more in a moment. Lower cure temperatures. Yes, we found that we were able to achieve this with BDMA. Levels that we were targeting before, and quite possibly even lower levels. Cure in less than an hour. Same thing. The best combination we found was not only with the tertiary amine, but also with this very novel blended curative that we produced for the study. One component systems, yes, this becomes and remains a challenge. The reason? Within these systems, there is always some amount of free acid. This is because of the curatives that are used. These mono and dianhydrides, through the manufacturing process, have a certain amount of free acid. This can be considered a contaminant, if you will. It can be considered a kind of a catalyst to begin the polymerization process. Has to be controlled. So from a shelf life standpoint, more work has to be done in that area. Latent systems, which are also very important in terms of shelf life stability. We found very interesting results with ureas, especially as they work with BTDA. We'll talk more about that. How about glass transition and TG development? With all the different systems that we went through, we found that BTDA works best by itself and produces the highest level that way. More on that in a moment. And what about degree of cure? Are you getting some things, and are you giving up other things? And the answer is yes. Depending upon the accelerator that you choose, you can influence cure speed, and you may have to sacrifice some degree of cure, and vice versa. So this was very interesting to discover, and we can show you more definitive data in a moment. Let's take a look at homopolymerization. What we have here is a comparison of different accelerators without the use of any curative. And the first obvious result is that we're getting cure in every single case. So homopolymerization indeed is prevalent. It is going to work against what you really want to achieve, which is an optimal formation of your three-dimensional network, your highest glass transition temperature, your highest level of heat resistance, and so on, depending upon what you're looking for. But we had discussed the curing mechanisms in past, and now we have phenomena here where homopolymerization can possibly dominate your curing process. If we look at the different performance from the accelerators, we see that BDMA induces the least amount of homopolymerization as measured by enthalpy. And what's more than interesting is that the ureas generate an incredible amount of enthalpy, which means you're getting a very high cure occurring, although it's homopolymerization. So these systems will all work, even without curatives. They're working against you in this case because you want to steer the reaction towards the desired result and away from this type of behavior. So it's important to see that the different accelerators influence that, in some cases more than others, and that has to be taken into account when you're building your combination of ingredients. Homopolymerization is an issue, and it's prevalent. Here are the results of curing with dianhydride as the sole curative, and there's a couple of takeaways here that I'd like to focus on. You've got the use of BTDA without accelerator producing the highest amount of enthalpy, and by definition, more thorough cure, and very likely the highest glass transition development. The issue here is that it's a slow system, and if you can tolerate that for your process, then you can achieve these very high levels that may be suitable for you. If you prefer a faster curing system, the accelerators help. In some cases, for example with BDMA, it certainly facilitated a much lower temperature, faster processing condition. You do sacrifice a little bit of enthalpy, so perhaps your degree of cure is not where you want it to be. It could also work for you because maybe you're manufacturing a thicker part where you prefer a slightly lower enthalpy and you do not want to induce a lot of process-related stress. So that may be the right system for you. When you look at ureas, on the right side, you see here that we actually got some latency, much longer onset, and we were also able to achieve a much higher enthalpy, which works in your favor towards degree of cure. So if that's the type of system you're looking to design, then you should look towards ureas as your solution. The imidazoles kind of ran in the middle of the pack here. There was really nothing nothing discernible to recommend them over the other systems. But if there's something here that works in your particular process, they may be the right choice for you. None of these were able to address the challenge of one-component systems because of the presence of free acid content. We had hoped that maybe we could produce some type of shelf life stable system, but we were not able to achieve that. We were able to overcome the mixing of various physical forms of components by gentle heating, as we described. So very interesting results, and depending upon what you're looking for, it's now a lot simpler to pick out the right formulation that suits your need. Having just looked at the BTDA data, now looking at the corresponding data for nadic methyl anhydride, you see a very different type of behavior. First of all, NMA as a monoanhydride of its class of monoanhydride is known to produce the highest TG development. And if you look here at this data, you can see that the accelerators play quite a major role in that cure development. On the left is NMA without accelerator, and you see it's a sluggish, slow system with very little enthalpy associated with it. As you look at the tertiary amines and the imidazoles, you suddenly see where the cure is being driven to much higher levels of enthalpy, in some cases even an improvement or a reduction in onset temperature. So you see a lot of benefits. To the right, the urea, which responded very well with the BTDA, simply does very little over here in combination with the monoanhydride. So the focus becomes the tertiary amine and the imidazole and the strong impact they have on driving the cure performance of the NMA. So this basically begs the next question. You've seen the performance of the BTDA, now you've seen the corresponding performance of the NMA, and it makes you wonder, is there a way to put these two systems together and give you the best combinations of both? This is something we'll show to you next. Here we have the data set for the blended curative. Does this represent the synergy, the super system that we've been looking for? Perhaps. There's a lot of interesting data here. What I'd like to draw your attention to is the result using BDMA with this blend. You can almost see the contribution of the monoanhydride and the dianhydride and how they work together. You've got a lower onset, so you've got a faster cure development. You've got a reasonable amount of enthalpy build, so a fair amount of cure that may be good enough for your particular process. It may be good especially for a bulk part or a thick casting. So this could very well represent a good compromise between your processing and your properties. So if we consider all of these data together, we can come up with the following key formulating tips. Number one, monoanhydrides greatly benefit from accelerators. You saw how they relied upon the accelerators to drive the cure. Tertiary amines and imidazoles worked well in that regard. Number two, dianhydrides, particularly BTDA, don't necessarily require accelerators for curing, especially if you're willing to tolerate the longer curing cycle. If you want to improve that, the best response was obtained either from tertiary amines or ureas. Number three, for the ultimate in TG development, cross-link density, BTDA is a very suitable candidate. Number four, if you seek a lower curing temperature, a faster cycle time, and overall more rapid system, tertiary amines and the dianhydride monoanhydride blend worked very well and served as a good compromise. Number five, if your goal is a latent system, BTDA and ureas provided a very nice level of performance. Number six, we identified homopolymerization in all systems. Is there a way that you can manage it? Can you control it? Can you discourage it? Can you impede it? Possibly. The best results were obtained by using tertiary amines. Number seven, for mass casting, prepregs, anything that maybe will build some heat during the cure cycle, consider the lower enthalpy afforded by BTDA and tertiary amines. That could also be the case with the blended system and the tertiary amines. And number eight, the one component system and the presence of contaminants, which will always work against you. These could be generated by the anhydride curatives and their free acid content. It could be the presence of contaminants. One-component systems continue to be a challenge. We're happy to share all of our data, and as a result, we were able to focus on some very encouraging results and others where there was room for improvement or the need for further study. Some of those are identified here. An isothermal curing study, which would be very helpful to better model the degree of cure of the faster curing systems and really kind of quantify and qualify them, perhaps even rank them in terms of performance. The one-component systems, we have discussed the shortcomings, the need to really understand contaminant effects, and that's an ongoing need. We've characterized the performance of these curatives and accelerators in DGEBA resins, but multifunctional epoxies can more than likely produce very different results, and it would be interesting to examine those. We've focused on TG development, on cross-link density, on cure efficiency, but we know we're moving in the direction of rigid systems, so a study of different types of tougheners would be very helpful to understand how we can offset that level of rigidity. Is a super high TG, is it necessary? Maybe a certain level is good, and it can be offset by tougheners to improve or reduce the rigidity of the system. That's a very interesting future work topic. We'd like to thank you for staying with us, and I really appreciate your interest in our work. I'd like to conclude today's webinar with a couple of remarks. Epoxy-Anhydride systems have an established track record, and you see their history dates back, several decades. There are some really sound legacy applications, and now you can see the interest in transferring some of that value into some of today's demanding projects. An understanding of their curing mechanisms, therefore, is vital, and how the different components behave is really necessary to understand in order to really extract the performance benefits that we're all looking for. DSC as a thermal analysis tool was proven to be really useful and really helped us investigate behavior, establish certain trends, and make recommendations, and we intend to do more. We certainly got a handful of encouraging results, and I hope that the key formulating tips we provided are useful to you and can benefit you in your projects and applications. This type of investigation really would not be possible without a true collaboration between we've involved multiple parties, different disciplines, different points of view, and in the spirit of open innovation, we were able to really come together and have very good discussions and generate these data sets, which I hope that you have found use in. We intend to do more, look for some additional productions coming from us in the near future. If you're interested in participating, or if you have further inquiries about what we've done, we more than welcome hearing from you. You may contact us at any time. We'll provide information for you and look forward to hearing from you. In the spirit of that collaboration, I'd like to acknowledge the various partners who have come together to make this study possible. First off, I'd like to thank Dr. Anand Rao at Crosslink Technologies, whose team has done a lot of this work and has contributed really wonderful ideas. Dr. Pritesh Patel at Evonik for providing his expertise on epoxy chemistry and accelerators. Dr. Vinay Mishra at Dixie Chemical for his expertise in monoanhydride systems. Dr. Jeff Dimmitt at Jayhawk, who's provided the expertise in our dianhydride systems. Thank you very much to our collaborators, and we're looking forward to doing more with you in the future. Once again, I'd like to sincerely thank everyone for your attendance at today's webinar. Really appreciate the interest that you show in our work. We're going to put together our collaboration team and field your comments and questions at this time and look forward to the discussion.
All right. Thank you very much, Boris, for that presentation. We already have some questions coming into the chat, so I just encourage everyone to get your questions in because we have some panelists here that are going to be able to answer those questions and give you some more insight. So real quick, we have with us to answer your questions. We have Jeff Dimmitt from Jayhawk Fine Chemicals, Boris Shafran from Jayhawk Fine Chemicals, Vinay Mishra from Dixie Chemical Company, and Anand Rao from Crosslink Technologies. So we have about 25 minutes to answer your questions. So if we don't get to anyone, don't worry about it. We will attempt to answer them offline and help get the answers that you need. Okay, so first up, we have a question from, or a comment. This says, and we're going to send this over to Jeff, anhydride reacts with an acid group 2. Jeff, can you speak to that?
Yes, I can. You are right. Anhydrides and carboxylic acids will react with each other. But the anhydride and the epoxy function will not interact. It's the carboxylic acid interaction with epoxy that is more of a concern about the stability of a 1K type or latent system when you're using anhydride initiators or cross-linkers for curing your epoxy.
All right, thank you, Jeff, for that. And then we have another question here that we're going to send to, I believe, Vinay and Anand. This is about the electrical, or this is why not consider the zinc derivative accelerators such as naphthenate.
This is Vinay Mishra. So I apologize. Actually, we haven't had a lot of experience with zinc derived accelerators, so we did not include that in this particular study. We're trying to basically focus on a very, very commonly used tertiary amine like BDMA, which we used, and imidazoles, which are also very commonly used for anhydride epoxy composites. And then we wanted to throw in a few other materials like the urea accelerators. So for this limited study, as our first step in this investigation, we did not include that, but we will certainly consider other materials in future work. Anand, feel free to comment from your side.
I might jump in here too with some comments. The use of metal organometallics like metal acetyl acetonates, but not actually, or historically going back into the 70s, the original cured accelerators that were used with BPA systems. So yes, they are it is very possible to use those and use those effectively.
All right, awesome. Well, thank you so much, guys, for that answering that question. So next, I have one that I believe Jeff can speak to, though anyone else can speak up. Is it possible to cure? Oh, I'm sorry. This is going to go to Anand. Is it possible to cure the systems at room temperature? Anand, can you answer that question for us? All right, we'll open that to the whole panel. Can anyone go ahead and see, is it possible to cure the systems at room temperature?
Sure. This is Vinay. I'll take that. So these anhydride epoxy systems, they do require elevated cure temperatures. And as we all know, there are options available for curing at room temperature. There will be amines, for example, that will cure at room temperature. However, for this study and these materials, unfortunately, room temperature will not cure them. We have certain types of anhydride systems that will cure at a moderate temperature, say 80 C, 100 C, but then you will not be able to get the high glass transitions with those cure profiles that are the intentions of this program with the BTDA and the NMA. So for the high TGs, you do need high temperature cures.
Yeah, just to follow up with what Vinay's comments, if you're using a pure, for example, BTDA curative, you really need to get upwards of 150 to 160 degrees so that the dianhydride itself will start to dissolve into the epoxy resin, which will then initiate the curing reaction to occur as it becomes a one-phase system. So without the use of an accelerator of some type to initiate that chemistry to occur at lower temperature, you're not going to be able to do anything at as low as room temperature.
All right, thank you, and thank you for all the questions that are coming in. We're going to be working through those. Have another one here. I'm just going to leave it open to the group so someone can just jump in. How does reheating, warming above TG affect the strength and longevity?
Hey, this is
Vinay.
Yeah, this is Boris. I'd be happy to chime in. I believe the questioner is basically speaking towards some type of post-cure, which we have not examined here. In some cases where you see the data where there is a certain degree of enthalpy generated, you can certainly drive that a little bit further, and that's that's something that we didn't look at in the study. We just wanted to go once through. So, I mean, the answer to the question is yes. You could drive some additional cure. Ideally, what we want to see is the extent of cure that we can achieve in a given cure cycle, and that's why we focused on that. If anybody else would like to jump in, to offer some additional comments, that would be great.
Yeah, this is Vinay. I'm assuming it's the question from Samson Lee. Is that right?
Yes.
Okay. Yeah. So and to add to Boris's comment, once you have cured it or post-cured it, the composite is basically a thermoset, as we know. And reheating, rewarming above TG, of course, it'll soften the product. So if it's in service, it'll soften to some degree. However, as long as it's not under undue stress, it would hold itself together. And it should be able to cool back down and regain most of those properties. It should be fairly reversible. Any effect on the property should be fairly reversible upon heating and cooling back and forth, unless you have gone to some very high temperatures where degradation may occur. So without degradation, temperatures should be fairly innocuous of a change.
All right, thank you. And then we have a follow-up question talking about TGs. Did you measure cured TGs of these formulations? Boris, do you want to speak to that?
Sure, yeah. I see the question's coming from Megan Casey. Hey, Megan, how are you? We measured TG on a spot basis on a variety of different formulations just to kind of check our work and see if the the analysis that we were working on, if it held out, and we got a TG number that validated that. So we did not do it comprehensively. What we'd certainly like to do as part of a future work, I had mentioned that we wanted to do an isothermal cure study and then do a formal evaluation of degree of cure and possibly even rank the systems. That's where I would love to include some additional TGs so that you have some definitive data for the various systems and how they compare to one another. So we did a little bit, but there's more to come. Thanks for the question.
All right, thank you, Boris. And then I have one from Nathan Phillips for Jeff. In your work, have you encountered or determined any reaction effects of the basic accelerators used with the anhydride that result in the form of carboxylite?
We have not seen any effects such as possibly described here. I mean, I can understand chemically why you would think an amine accelerator might end up with forming a carboxylate salt, but I believe what's happening here is that the amine's going to open up the anhydride ring, and then that's going to then kick off the epoxy curing reaction. And by the time the curing reaction is completed, I don't believe there's going to be any free carboxylates left that could form salts. Anybody else want to follow on with that?
Hey, Vinay and Ann, do you have anything to add?
No, not me, but hi, Nathan. Good to have you on this webinar. No, that's something we just didn't have as a focus of this study at this point, but perhaps in next phases we can tackle that.
Okay, we got another question here. This is from Jose. What was your anhydride epoxy ratio used for this study? Boris, do you want to speak to that one?
Yeah, sure. If you go to if you take a later look at the design of experiments page where the 12 formulations are laid out, you see the basic data in PHR. The 80 ratios I don't have on that chart. I can supply that to you. But basically what we did is we measured straight to the theoretical amounts based on stoichiometry, and then we backed off considerably. So actually, I'd be happy to follow up with you and send you those data so that you see exactly where we ended up with regards to AE ratio. But suffice it to say right now, we are not at 1-to-1. We have backed off. And the reason you really need to back off is because of the high reactive nature of the mono and the dianhydrides. If you stay on stoichiometry, you're going to create a system that either it runs away from you, it does not cross-link correctly, and if you slightly back off, which becomes more of an empirical kind of an area now that you're working in, you're not spot on with the chemistry, it actually responds better. So I'm happy to follow up with you offline and provide that information to you. Thanks for your question.
Boris, I may just follow on with a couple of comments on that. Yeah, the consideration is the understanding needs to be that BTDA is a tetrafunctional curative, and so if you, as Boris indicates, if you're on stoichiometry, your cross-linking gets so extensive that in the end you actually will end up with a material that can be quite brittle, and so that's really what's driving the need to be off stoichiometry.
All right. And thank you guys for bearing with my terrible pronunciation. You have a layman kind of doing the moderating today. So I got another question here from James. It's, what system would you recommend for syntactic expandable foam core with a pre-preg outer layer? I'm just going to leave that up to the group, whoever wants to pick up on that. Thank you.
Okay, this is Boris. I can jump in and start that discussion. We have actually done quite a bit of work in the area of syntactic foam, and we have actually focused on the one curative system that we referenced here, which is the BTDA NMA blend with BDMA as curative. We got some very interesting results, and there are some previous webinars that we have hosted which speak to those. Actually, we did 2 of them, and if there's more information you'd like regarding the how to put the formulations together, we'd be glad to speak to you offline. But yeah, we've got a really nice data set. We worked with all the colleagues here in the panel, and that is available. Would anybody else like to add on?
Yeah, this is Vinay. Boris, very well covered. And James, basically, based on your application, there are a variety of formulations that can be offered between BTDA, NMA, and other monoanhydrides in combination with BTDA for that matter. So it all will depend on what your specific requirements are, but there's tons of information available for those types of applications.
All right, thank you guys for that. And again, we just really appreciate the participation. If anyone else has any more questions, we do have about 10 minutes that we might be able to squeeze it in. So just keep them coming. Really appreciate it. We got another one here. Boris, can you answer this one? Can prepreg be formulated with epoxy-anhydride systems?
Yeah, thanks, Eric. As a matter of fact, yeah, we've got a couple of customers that are now starting to look at this, and basically what it draws upon is the legacy work that I mentioned, especially the electrical applications and the coating powder applications. You've got a lot of similarities there where you're creating a B-stage product that has to sit with a given shelf life before it's activated and used in a subsequent process. So we've got a couple of customers that are starting to look at that because they'd like to take advantage of a fiber-reinforced composite for, let's say, an underhood application. So a lot of things draw from that. The references I made to contaminants, free acid, things of that nature all have to be kept in mind because now you're looking at a shelf life issue. We've got customers that put together very reasonable systems, but that work continues to be done. That I would consider to be one of the newer areas that people appreciate this legacy work of the epoxy-anhydride cure and want to take it towards new applications. And prepreg for fabrication of parts for automotive underhood is a really hot topic right now, and we're doing our best to support those customers. If anybody else would like to chime in, happy to have your comment as well.
Boris, I'll just follow up a little bit and comment that you're exactly right. There was some concern initially that these formulations would not work well in a prepreg type application, but as you commented, the limited work we've done has shown it to be quite doable. That the fibers themselves don't act to separate the two-phase system. That the two-phase system is fully integrated into the fiber, allowing a good cure to occur when the system's cured. As Boris comments, we have not looked at shelf life stability on these systems, but in terms of a short term where you would impregnate and follow up in a relatively short period of time with a cure, the systems have worked well.
All right, thank you very much. Unless someone else has anything else to add, Anand, did we get you on the line? Okay, well, I'm going to go to another question here. Vinay, I'm going to send this one over to you. How do I know I've achieved the right balance between processing and properties?
Oh, yes. Okay. That's a good one. So really, this is a multi-step process. I'll share my opinion and certainly would appreciate comments from my colleagues on the panel. But my view is that it's best to just start with the raw materials supplier's recommendation on the final properties, at least because the raw material suppliers typically are able to find the process conditions which will lead to the maximum performance. And once you at least know what the capability of the performance is, you can run those formulations or suggested formulations to your process that you know you use is ideal for you. And then look at the results. If the results in performance are somewhat lower than the ideal maximum, then you can look into whether that level is sufficient for your application. If it is, you're home free. But if you do want to improve from that level of performance closer to the maximum that you know is capable for the system, then the only step I'm aware of is that you got to run some process experiments by varying the process variables to the degree possible for your operation, and just do that study. And it all depends on what's your cost parameter. What are your cost parameters for your process? So every process change adds some cost. So the best thing is to just make really keep track of those costs and time parameters that you are starting to add to your process and compare them with the process. Anyone with comments?
Yeah, this is Boris. I'm in agreement with that, and that's pretty much what we wanted to demonstrate today, especially with the inclusion of these different accelerators to show how you can achieve that balance. There's a lot of give and take here, as you can see, and it depends what you're looking for. If you're looking for a high TG development, you have to steer towards certain accelerators, or actually, in some cases, no accelerators. If you're looking for faster cure or lower temperature cure, you've got to swing back and start looking at those different families of accelerators in terms of what you need for your process. Maybe even your own processing conditions are the dominant factor. What your current process can do with regards to how high can you dial the temperature, how slow can you run your line. Those may be the limitations too. So this webinar really was to kind of generate food for thought, and there is additional work that we want to do. And there are further productions that we're going to do on this. So, please follow us, because there'll be other things that we'll be presenting in this same, the same type of subject matter later this year.
All right. Thank you so much, Boris. And we are out of time, so I think it's time to wrap it up. Does anyone on the panel have anything else they want to add? All right, perfect. Well, thank you so much to everyone that's been a part of this webinar. The fact that you guys were giving us feedback and questions really helps. It's really awesome to have just some time to dig into this a little bit deeper. So that is all the time we have for you today. Thank you again so much. Take care, and we will be talking to you soon.